The structure in this example is a hemiacetal. Recall that the difference between acetals and hemiacetals is that the hemiacetals have a hydroxyl group. So this look for that hydroxyl group. Upon elimination of an alcohol, that would be ethanol, which we can see here. The carbonyl compound that is formed is an aldehyde that has 4 carbons, so that would be butanal. One, two, three, four. 1, 2, 3, 4. This reaction does not require any other stoichiometric reagents. It's an elimination reaction, and it can be catalyzed by either strong acid or by strong base. So we'll look at both of those options. Let's look at the acid conditions first. The reaction that we're trying to explain is an elimination of the ethoxy group, and so that's the group that we're going to protonate. So this is our example strong acid. You could use a different strong acid, H2SO4 or HCl would work the same way. The acid protonates the intended leaving group. It is now a good enough leaving group to get kicked out by this neutral oxygen lone pair. And we have one final step, and that is that whatever the conjugate base was of the acid, so in this case I've chosen hydronium ion as the acid, so water as the conjugate base of it is going to deprotonate the carbonyl and give the neutral aldehyde product. We can draw the reaction in the reverse direction and make sure our intermediates line up. So here's the aldehyde starting material. Under strong acid conditions, the strong acid is the hydronium ion again in this example, we would activate the carbonyl by protonation of the oxygen. That gets us to this intermediate, which can then get attacked by the ethanol molecule. The ethanol molecule comes in and attacks the carbonyl carbon, breaks the pi bond towards that positively charged oxygen. So here's the new oxygen with the ethyl group on it, and it still has hydrogen attached, so it has a positive charge. And the conjugate base of the acid that I used, of the strong acid that I used, is water. So the water can act as a base and gets us back to the hemiacetal. This reaction could also be done under base conditions. So for our example, we will use hydroxide as a base. And so here's our starting structure. The hydroxide ion as a base is going to come in and deprotonate the hydroxyl group. That provides a minus charge, a strong reactive site on this molecule, and that reactive site is now strong enough to push out the neighboring ethoxy group as an ethoxide ion. That ethoxide is a poor leaving group, and so we needed the negative charge on the adjacent oxygen to help push it out. The stability that's being gained is from creating that carbon-oxygen pi bond. So here's the ethoxide. I'm going to put it over here to make sure we're not getting ourselves confused. It was a product from that step. If we're thinking about the base being catalytic, we have two options. To show that we only needed a catalytic amount of that base that we used, the hydroxide. Option 1 is to regenerate the hydroxide. And so we can show that by saying that this ethoxide is going to act as a base with the water molecule that was generated when hydroxide acted as a base. Right, so when we used hydroxide as a base, we created its conjugate acid, water. And we can show that this reaction generates the alcohol we're trying to explain as a stoichiometric reagent, and the hydroxide ion that we're trying to explain as a catalyst. And so we come up here and compare and say, this is one way that we've fulfilled the overall goal of demonstrating how the alcohol side product is made, and that we've created the same base that we started with, and so that base was catalytic. The other option for how to show that that only a catalytic amount of the base was needed is to show how the new base that was formed can act as the new catalyst. How it can take over the role that the hydroxide was playing. And so the way that we would do that is we would say this base that was formed can come back over here. And we can say that an alternative to the original step was that the ethoxide ion acted in the way that the hydroxide was acting. Okay, now that we've talked about the catalysis here, let's talk about the reverse direction of the reaction. So if we're talking about the reverse direction, and I'm going to line this up backwards again so we can compare and make sure we're hitting the same structures. Here's our aldehyde. We're going to go ahead and use the ethoxide ion as a nucleophile. That gets us to this charged intermediate, which can act as a base for an ethanol molecule. So the stoichiometric alcohol, that's a reactant if we're thinking about it in this direction. gets us back to the hemiacetal.